Dear students, today we are going to see an important topic in machine learning, that is PAC learning, right? So from the name we can see what is this PAC learning. It is probably approximately correct learning, right? So probably we can say it as like a probability and approximately correct learning. Okay, so that is how we can just expand PAC learning, and this is a framework. Okay, so in a machine learning, mainly it defines the conditions under which the hypothesis class H can learn a target function F efficiently. Okay, so that is the main thing. So here we have two important parameter. That is, one is epsilon, and another one is delta. So delta we will consider it as like a high probability, and then we can say this epsilon as like error, which measures the less error, means we can say the maximum accuracy. So we are using the epsilon is an another notation. Okay, so we are going to use this notation to bring approximately correct learning, right? So that is the main focus of this PAC learning. So from the name, we can see P, that belongs to probably. That means refers to the likelihood probability that the learning algorithm that succeeds in finding the good hypothesis. Okay, so we can say that parameter. Okay, so delta, where 1 minus delta, that represents the confidence level. See, for example, if you are saying the value of delta is 0.05, that means 5%, right? So if it is like this, means if the confidence level is 5%, then we can say remaining 95% chance that the learn hypothesis performs well, right? So this is how we will calculate based upon the delta value, right? Okay. So approximately means maximum, to the maximum level, if it is correct. So if you want to measure like that, means we can see the epsilon value as 0.01. That means the error rate is only 1%. Okay, so or less than 1%. So we can say such hypothesis will be considered as very good hypothesis, okay, because the error rate is very less, right? So that is how we will say approximately correct. Okay, so we can see in the example, binary classifier to distinguish between the apple and the orange. Okay, so based upon the features of color, size, likewise, we can just classify the fruit, whether it is apple or orange. Okay, so that is how we are just finding out based upon the features. Okay, so what is this PAC setting? Here we have the hypothesis class, linear classifiers. Okay, so as you know, the linear classifier, the straight line. Okay, it will separates or classifies the different items which is there in the data sets. Okay, so the target concept, how we are going to map, okay, and we are going to classify into apple or orange. That is our target concept F, and the goal is finding the hypothesis, that is H, that errors should be less than epsilon with the probability 1 minus delta. That means it should have a minimal error rate. Then only we can say it reaches to the maximum probability. Okay. So now consider the learning process. So consider like training the model on 100 samples of apples and oranges, in which the classifier achieves 95% accuracy. So automatically we will know epsilon, that is the error, is 0.05, that is 5%, right? Or unseen test data, that's less than 5% probability, that is del, which is equal to 0.05, right? Because 5%. That's the performance occurred by chance. The model is PAC learned. Okay. So this is how we are telling the PAC learning. Okay. So how we are going to tell based upon the probability value, right? Okay. So now let us see the example based upon the height and weight as a parameter. Okay. So the features of the data set. Based upon that, we can easily measure whether the person is fit or not fit, right? So based upon the height and weight of an individual. So that will be some restriction, right? With this height, okay, so weight should be like this. Okay, and we can say the result target as is a fit person, right? So based upon the features, what we are going to have, right? So that is how we are going to have. And when you see here, you can see the rectangle plane, we are using it to separate. Okay, so if you are having height and weight in x-axis and y-axis, if you are just plotting based upon the data set value, okay, which was given in the data set. So based upon that, if you are just finding out this is the corrected output, okay, corrected output. If you are just putting, okay, so the rectangle little up or down, okay, so how we are going to tell, okay, so the how to find the differentiation. For example, this is actually the we are predicted, right? And then we are using the model, okay, we are getting like this. That means what? If any data which is present here for this particular rectangle, we can say it is correct, but it is out of the box. Got it? So we can say that false positive and false negative. So we can see that this is false positive. Okay. So false positive. So if any because that exceeds with the box. So if any plus coming here, it will think in their mind that it was trained and it was belong to this particular category. But when you see in our example, we can see that we are going to calculate the false positive. Okay. Similarly, we can say that false negative as well. Okay. So this is, we can say it is like a false negative. This is the actual value. And then we can see here it, uh, when we look at it, both, okay, rectangle what we drawn is looking correct, but only based upon the value. Okay, whether we are using the value, and based upon that, we are going to find out whether it is a false negative. Okay, because this is not fit in it. For example, if here plus are coming, okay, so it will feel that, okay, so which is correct, okay, but actually which is not correct. That's why we can say this is the false negative. Okay, and this is false positive. The mainly the rectangle which exceeds the point, okay, or otherwise it will reduced. Okay, so that is the time false negative we will say. Okay, so for this, what we are using this formula is P of C XR of H. Okay, so with hypothesis and with C, okay, we are making an XR of it, and we should be less than epsilon. So that means minimal error. Okay, so if you are finding out, so that will be the calculating the performance, right? Okay, so the goal mainly to achieve the low generalization error with high probability is we can give like this. Okay, so that is probability of error of H, okay, which is less than epsilon. Okay, so epsilon, which is greater than 1 minus, okay, delta. That is how we are giving. Okay, so that means probability of P of C, okay, XR of H, okay, that should be less than the error rate. Then only we can say it is a high probability, and which is greater than 1 minus delta. Okay, so that is how we are going to get the goal. Then we can say this is the best criteria, right? Okay. So when you see this particular figure, colorful figure, we can see that height, which is in the x-axis, and weight in the y-axis. And you can see some training samples in which we are going to find out, okay, whether the plotted thing is right or not. So here you can see that all this greenish part, it comes as green, and the training from the training sample, and in the red we are going to show the target, right? Okay, so here this is like one training sample, right? And coming to the second all green. Okay, we are taking it out. Okay, and then the next again we are having the different groups. Okay, so up to weight and height we are finding out to the n data points. Okay, so that is how we just plotting now. Okay, so based upon the final outcome. See, now we are going to see how the hypothesis H1 and H2 will be calculated based upon the data set what we have given, right? Okay. So in this, this is the height and weight we are taking from the training sample and we have plotted it, okay, using graph, we have plotted it. And now when we consider the error of H1. Okay, so we are finding the threshold as 0.05. Okay, and then that is how we have fixed. Then only we will get, okay, the best quality value, right? So here we can see that 0.09 and 0.06 that exceeds 0.05. Okay, so here we have fixed the error rate as 0.05. That means what? Whichever things which exceeds this particular value will be considered as like an outlier, or we will see, okay, what we are going to do. And delta, we are giving 0.20. Okay, let us see how we are finding the probability of H1, hypothesis H1. How we are finding means out of 10 data sample, 2 is, okay, so abnormal. So we are taking 8, that is 8 divided by the 10. Okay, so that is the total number of data samples. Okay, we can say this is 0.80. And then again, we can see the probability of H1 in which we are going to calculate. Okay, so we are finding it out and then we are finding out based upon the 1 minus delta value, that is 0.20 we have given, right? We have to check. If this value satisfies, then we can say this is approximately correct. Got it? Okay, so the range is less than, so we can say that which is equal to. So here also 0.80, okay, and we can see that we can say the probability approximately correct. Coming to the second sample, if you look at it here also 0.05, the value which is given, and delta is 0.20. Okay, so with this, this is the data points. Okay, data points. So when we are taking here all the value, okay, so which are all the things which is abnormal, that is more than 0.05, that is 0.06, 0.059, okay, 0.55. This is also very much high. Okay, 0.05 and this is 0.55, right? All these three we can say it is abnormal. So total number of data element we can put it as like 10, and then we can see that in around for 10 we are having three values, okay, which is mismatched. So we can see that 7, okay, 7 by 10. So 10 minus 3 is 7. So we can put 7 by 10. Okay, and then we have to calculate with 1 minus delta. Okay, so that is 0.70, which is less than, okay, 1 minus 0.20. So we can say it is not probably approximately correct. If that condition satisfied, then we can say it is probably approximately correct. That is PAC. But in this example, we can say it is not correct. Okay. So mainly the importance of PAC learning is even it can generalize well. Okay. Even from the limited number of samples, but the accuracy and the confidence level. Okay, how much we are increasing the samples, that much we can increase the performance, right? Again, the PAC framework is a basis for analyzing and designing many machine learning algorithms. Okay. And thirdly, we can see that how we are going to access the reliability and robustness of this algorithm. When we are going for this PAC learning, you can see how many advantages are there at the behind the scene, right? And then by understanding the PAC learning, researchers and practitioners can develop more efficient and effective model. That is also one of the important key factor of PAC learning. Okay, importance of it. So when we just look at the core concept of PAC learning, we have epsilon and then confidence, that is one minus the, okay, delta, and then higher accuracy, higher confidence, complex hypothesis space can be dealt with, Whenever we can see with notation, with more samples, then we can get the accurate result. Okay, so that is the main thing we should always think about, right? Okay, and then we can see about mainly the hypothesis space. Always there should be less overfitting and less underfitting. So that have to be reduced. Then only the overall performance will be more, because it will calculate only the training sample, and the unseen data when it comes, it will not be clearly measured, right? So that's why we have to reduce the underfitting and overfitting to improve the performance. So that is very important. And then in generalization, again, we can see the ability of learning algorithm to perform well on unseen data. Okay, so that is the main focus of going for this pack learning. Okay, so in everywhere unseen data when comes, it will not able to predict correctly. Okay, so here it does to the maximum, right? And pack framework mainly it is quantified by the probability that the hypothesis will have low error rate. That is the main thing. Low error rate on new samples, especially. Okay, how we are going to handle the new samples. Okay, and then the low error rate also should be low. Okay, and then the main important is this model is in the real world application, right? Making the accurate prediction on new data. Okay, these are all some of the features already we have saw. And PAC guarantees, that is, it provides the theoretical assurance that the hypothesis will generalize well on unseen data. Okay, so that is the thing, again and again we are just stressing it out. Okay, the main key points of PAC learning theorem. So we can see here the performance landing mainly in terms of the accuracy and the confidence. So delta, we can say it is like a confidence, and accuracy, we can say it as like epsilon. That means what? It will have low value. Okay, so that is how we are going to calculate, right? And then when you see how the mathematical expression will be written, so if m is the sample size, okay, and then epsilon, that is the error rate should be minimal, okay, and then delta, okay, as a probability value of it. Okay, so that is how we are just going to do an Vapnik Savro-Nenkin dimension of the hypothesis space, that is VC. Okay, VC of H. So in that hypothesis H, how this dimension is working, right? Okay, so I hope you understood the pack lining theorem. Okay, so that's all from the module one, and in the next we will see about the module two. Okay, so I hope you understand clearly about this pack learning as well. Okay, so easily you can understand the concepts. Thank you, students.